We now take a look at a couple of problems from your text, the first one of which is 413. Here we have a frame, ABC, that has a frictionless pulley at C around which a cable is wrapped. The frame is secured by being built into some foundation here at A, and we know that the moment produced by the cable forces at A is not to exceed 20 kilonewton meters, and on that basis we're to determine the largest weight W that may be supported and the value of alpha for which the moment about A is the largest. Pause the video now and try this problem yourself. Resume playing when you're ready to see a solution. So we know that we need to take moments about A, and the question is, what's the best way to do that? This problem is complicated by the fact that we have this pulley mounted at the end of the frame at C, and it has a radius that's not trivial. So we essentially have two choices here. We can leave the pulley on the frame and proceed to analyze the problem that way, or we can first begin by drawing a free body diagram of the pulley and determine what sort of forces are exerted at the bearing at C, and then an equal and opposite set of forces will be present on the pin at C acting on the frame. And that's the way I'm going to proceed. So I'll just remind you, if we have a pulley, here's its center. It's free to rotate about that center, but we can't move the bearing through the pin. And so what that means in terms of reaction forces at C is that there will be a CX and a CY. And then we're cutting through the weight over here, and at this angle over here, this is alpha. So the tension in this case is going to be just equal to the weight if it's a frictionless pulley. So I'm just going to replace this with W and W at these two locations. And in our previous discussion of the pulley, what we said is that these reaction forces CX and CY have to balance the forces that are exerted by these weights. And even though we could leave it like this is equivalent to saying that those forces CX and CY have to be equal and opposite to these two cable tensions. So we have a W like this and a W like this. This can be useful in terms of looking at what's happening to the frame, because if we have these forces that are exerted on the pulley bearing by the frame, then we have equal and opposite forces exerted on the pin on the frame. So this amounts to essentially transferring the original forces that are applied on the outside of the pulley directly to the pin at C. So now we want to know what moments these exert about A. So here we have a position vector that goes up to point C, and we can see from the geometry of the figure that this is a 3, 4, 5 triangle. The moment that the vertical component exerts about A is going to be a fixed value. It's going to be the weight times 3 meters. If we're interested now in an angle alpha that will maximize the moment about A, then what we're doing is we're looking for an orientation that is perpendicular to this 3, 4, 5 triangle. So this is essentially going to determine what value of alpha we're looking at. So if we have a 3, 4, 5 triangle like this, then the orientation of alpha will be such that we have a 3, 4, 5 triangle like this. This will be perpendicular. The slopes are the negative reciprocals of each other. So here now is our preferred orientation for W that maximizes the moment. We have this corresponding value of alpha, and we can see that alpha is the arc tangent of 4/3, and that turns out to be 53.13 degrees. With this value of alpha, the moment about A is maximized, and we can see that at angle alpha, the moment arm is going to be 5 meters. For the vertical segment, the moment arm is 3 meters. So our criteria is that W times 5 meters, and we should mention that both of these moments are counterclockwise or positive about A. W times 5 meters plus W times 3 meters has to be less than 20 kilonewton meters. And if we solve for W, that ends up giving us that W has to be less than 2.5 kilonewtons. For our second problem, we're going to take a look at problem 422. We're asked to take moments about 2 different points, and I'm just going to focus on B. We're going to take moments about point O. This problem in the companion problem 423 asks you to take moments about one of these 2 points using either the scalar or the vector approach. I'm going to take a slightly different approach. Instead of looking at a problem and saying, well, I'm going to use either a scalar approach or a vector approach, I'm going to look at individual force components in the problem and ask, are these easier to deal with in terms of a scalar approach, or are they easier to deal with in terms of a vector approach? And I'll use the approach that I think is most convenient for each force component. Okay, so I'm going to treat these 3 forces sequentially, and the easiest one to deal with of these 3 is P, because the moment arm from O to B lies along the z-axis, and P is obviously in the minus y direction, and we can see from crossing the position vector from O to B into P that we're going to get a resultant moment here that lies along the x-axis. So this is a force which is easily dealt with using a scalar approach, and I'm going to just write it as the moment due to P about O is the moment arm of 16 inches times 100 pounds and it's going to be in the I direction. Okay, now the moment that F contributes about O it's kind of on the border. We could use the scalar approach or we could use the vector approach. If we look closely at the geometry of this position vector from O to D, we'll note that this is a 5, 12, 13 triangle here, and if we perform this operation of crossing R into F, we're going to get a moment that's in this direction, and again this will be a 5, 12, 13 triangle over here. So we can say something about the orientation of this moment using the scalar approach quite easily. Here we're going to have that the moment due to the force vector F is the moment arm, and it's actually 39 inches times the force is 200 pounds. And then that's on a unit vector UF, which is given by the 5, 12, 13 triangle that we can see down here. UF is going to be equal to 12 thirteenths in I and minus 5 thirteenths in K. Now that's using the scalar approach. Alternatively, we could use the vector approach, and there we would write the moment due to F about O would be ROD cross F. And that's again 15I plus 36K crossed into minus 200J, and that's in units of inch pounds. And that ends up giving us 15 times 200, we have minus 3,000 of I cross J, and we have 36 times minus 200, it's minus 7,200 K cross J, And that result again is 7200 I minus 3000 K inch-pounds. And we can verify that this result is the same as this scalar result that we have here. Now the last contribution is due to this 50-pound tension that is pulling from C to A. The fact that we're going to have three components of tension, three non-zero components of tension in each of the three directions makes it a more three-dimensional problem, and I would generally not advise using the scalar approach for a problem like this. So here I'm going to forego the scalar approach altogether and write that the moment due to the tension T is equal to ROC cross the tension on the unit vector from C to A. The position vector from C to A is 12I plus 18J minus 36K inches. The length of RCA is 42 inches, and that gives us a unit vector along CA, which is RCA divided by its own magnitude, and that turns out to be 2/7 I plus 3/7 J minus 6/7 K. The moment due to that tension becomes 36K inches crossed into 50 pounds on this unit vector. And we can write that as 3600 over 7 K cross I plus 5400 over 7 K cross J inch-pounds. And the result of that is 3600 over 7. K cross I is J, and we have minus, the result of K cross J is minus I, so we have 5400 over 7 in the minus I direction. And then what we can do is take all these individual contributions and put them together. The resultant moment about O is the sum of these three contributions. So we have 1600 I plus 7200 I minus 3000 K plus 3600 over 7 J minus 5400 over 7 I inch-pounds. And this gives us a final result of 8029I plus 514.3 J minus 3000 K inch-pounds.